Let's build a logistic regression model in Python to help you better understand how it works. Let's start by picturing the exact type of problem a logistic regression model is meant to solve. Imagine that you are a doctor in a busy clinic and patients keep walking in all day with something that might be serious but also could just be nothing. You care about every single person, but there are obvious real-world limits. You cannot order the most expensive, time-consuming test for every patient. You need a faster and more efficient method that decides who needs the most advanced testing right now and who is probably safe to treat with basic care. So you decide to use the superpower that is machine learning and get planning. Say you want to predict which patients have diabetes. The first thing you notice is that your prediction is basically a yes or no outcome. Either the patient is diseased or they are not, and you don't want the model to be giving you weird outcomes like the patient is 1.6 diseased or negative 0.2 diseased. What you actually want is a probability that sits between 0 and 1, and once you have it, you can customize it for your clinic. If the model says the probability that a patient has diabetes is very high, then you order the advanced test immediately. If it's very low, then you might choose reassurance and a follow-up instead. Logistic regression is the machine learning method that was built for this exact type of problem. And that's because it's designed to turn a yes or no answer into a probability that you can use for decisions. So let's break it down. Now imagine just one patient walking in. You record some of their medical details, like their age, whether they have a fever, some lab values like blood glucose, and whether they're suffering from excessive thirst. These are the inputs to the model. Logistic regression treats each one of these numbers like a clue and gives each input a number called a weight. And the weight number is how hard this specific input pushes the prediction. Now, what do I mean by this? Well, if the model has learned that high blood glucose is a really strong sign for diabetes, then the weight on that input will be very large and positive, meaning a higher glucose value will make the model much more likely to predict that the patient does have diabetes. If the model has learned that a patient's fever doesn't really come in handy when it comes to predicting diabetes, that input's weight will be very small and close to 0. It will barely change the model's risk score when it comes to predicting diabetes. To combine everything, the model multiplies each input by its weight and adds them all together. And the model also has one extra number called the intercept, which is kind of the starting point before the model has any patient details. To combine everything, the model adds this weight input concoction and the intercept to get an overall risk score that the patient has diabetes. When this score is positive, the model thinks that the disease is present. When it's negative, it thinks that this disease is not present, and when it's around 0, it's kind of on the fence and neutral. At this point, this overall score is not a probability, and logistic regression is strict about that because a risk score can be any number, but a probability sits between 0 and 1. So logistic regression takes that overall score and passes it through a special curve called sigmoid. The sigmoid is a smooth S-shaped function that turns any real number into an output between 0 and 1. When the overall risk score is very negative, the sigmoid output will be close to 0. And when the overall risk score is very positive, the sigmoid output would be very close to 1. And after this step, we finally get the number we care about, which is the estimated probability that the patient has diabetes. So you might be wondering how the model learns to get all of the correct weights, because they certainly don't pop out of thin air ready to go. This is where the model's training comes in. So imagine you have a very large record of past patients, and for each patient you have their medical details. These are the features or the inputs that the model will take in. Along with this database, you also know the true outcome or target, which is a 1 or 0 representing if the patient has diabetes or not. And patient by patient, the model starts learning by making any prediction and being harshly corrected by the model. It uses a loss function that punishes the model, especially when it's both confident and wrong, because those cases are extremely dangerous in medicine. If the patient truly had a disease, but the model predicted they didn't, that is a huge loss, and the model receives a huge punishment. If the patient did not have the disease, but the model predicted a huge probability that they did, that's also a problem because of wasted resources, and the loss there is also pretty big. If the model was a bit uncertain and just slightly off, then that loss is smaller and more fair. But essentially, the loss function tells the model how wrong it was. Now, once the model has received all of these harsh punishments, it needs a systematic way to adjust the weights so that next time it's less wrong. And the model goes through this continuous cycle of receiving the punishment, adjusting the weights, and trying again. And that is the training part. So if the input of blood glucose continuously keeps coming up in cases where the patient did have diabetes, the model is continuously getting nudged to give that feature a positive weight. And vice versa, if some feature tends to appear in healthy patients patients, then that feature will get a negative weight. After enough training, the weights actually settle into values that reflect the clinic's historical reality. And now that these weights are frozen and good to go, every time a new patient walks in, we can just run their features through and see what the model outputs. And now it's time to choose a threshold, and this is the number that will transform your outputted probability into a yes or no answer. Does the patient have this disease or do they not? If you choose a threshold of 0.5, then all probabilities above 0.5 predict the model does have diabetes, and vice versa, all predicted probabilities below 0.5 predict the patient does not have it. So you choose the cutoff based on the trade-off you're okay with between catching more true cases and avoiding more false alarms. And that is the logic behind a logistic regression model. So if you enjoyed this video, then don't forget to follow so that you don't miss part 2, where I'll be scoping out this entire sequence of steps in Python. I'll see you then.